Good morning, everyone. In this video, I share with you the presentation I made at the AFROS conference. AFROS is the International Conference of the African Federation of Operational Research Society. My work is titled A Survey on Lightweight Block Ciphers for Data Security in IoT. I'm lecturer in Computer Science Department at Saïda University, and I am also a member of GECODE laboratory. I will start my presentation with a brief introduction to IoT and discuss the big security challenge in IoT and explain the existing solution, which is based on lightweight cryptography. Next, I will explain the aim of my study and give the obtained result with discussion, and finally I conclude the presentation. The Internet of Things is a network of interconnected physical devices, vehicles, appliances and other objects, embedded with sensors, softwares and connectivity features. These devices can collect and exchange data, enabling them to communicate with each other and with users. As more devices become interconnected, ensuring the protection of data become very crucial. The IoT presents big challenge related to data security because of the limited resource and security in the IoT. In fact, many IoT devices have limited computing power, storage capacity, and energy resource. All these constraints can affect their ability to process and transmit data efficiently. These limitations make the traditional cryptographic algorithms such as AES, DES, and 3DES, for example, unusable. It's become important to optimize algorithm in order to accommodate this limitation and ensure the smooth functioning of IoT systems. Lightweight cryptography plays a vital role in securing IoT devices, where efficiency and resource optimization are critical. This kind is defined by the following point. They are designed to efficiently protect data with low resource consumption. They provide strong security while minimizing the computational and memory requirements of cryptographic operation. They achieve a balance between security, efficiency, and resource usage, and are optimized for low-power devices and often employ techniques like resource size, simplified operation, and efficient implementation. There are mainly 4 types of lightweight cryptographic primitive. As presented in the figure, the lightweight cryptography primitive can be classified as lightweight block ciphers, lightweight stream ciphers, lightweight hash function, and elliptic curve cryptography. Each of the 4 types is based on different goals. For example, in the lightweight block cipher, the researcher tries to reduce the block size, reduce the key size, and create simpler round, and finally design simple key schedule. In this work, we focus on lightweight block ciphers, LWBC algorithm. To achieve the goal, researchers have focused on developing algorithms with smaller code size, low power consumption, reduced memory requirement, faster execution on constrained devices. Numerous work and studies have been done to satisfy the requirements of lightweight cryptography. For example, we have Present, Simon, Speck, Camellia, Clefia, etc. And all these references are mentioned for those who want more detail. The objective of our study is to evaluate and compare the performance of some chosen symmetric block cipher algorithm in IoT devices, such as Present, Simon, Skinny, Spec, and Xtea. The comparative analysis have been carried out in terms of time execution. For our test, for example, we choose two platforms, ASUS Notebook PC and the Raspberry Pi 3 Model B. This last one is well known as a pocket-sized computer system and is widely used as an IoT devices in literature. The characteristic of these two platforms will be well described later. Here, the chosen lightweight symmetric block cipher algorithm are defined and discussed. This table summarizes the comparison based on their block size, key size, number of rounds, and structure. Present, chosen lightweight symmetric block cipher algorithm operate on 64-bit block and support key length of 80 and 128-bit. It is based on 31 or 34 rounds of substitution and permutation network. Depending on the key size, the round function of present is based on SPN structure. Simon and Spec are two lightweight symmetric block cipher algorithms developed by the NSA that were developed by the National Security Agency. They operate on different block and different key length. They are based on a Feistel network structure with a specified number of rounds based on the key size. Skinny was developed by researchers at the University of Luxembourg and INRIA in France. It depends or its present also different configuration and is based on SPN structure. Xtea is an improvement of TIA. It is a simple and efficient algorithm. It operates on a 64-byte block size and a 128-byte key size, and is based on Feistel network structure with 64 rounds. Here we describe the two structures SPN and Feistel. Both are shown in the picture. In SPN, the entire plain text is processed in parallel. So in Feistel network, the plain text is divided into two equal halves which are processed iteratively through multiple rounds. In SPN, the encryption process involves multiple rounds where the plain text is subjected to substitution and permutation operation with k-mixing at each round. In Feistel network, the encryption process involves multiple rounds with k-mixing using a round function that acts on one half of the block at a time. In SPN structure, the substitution and permutation operation are applied together as separate steps within each round. So we recall that the substitution involves replacing bit pattern with different value based on predefined substitution table named S-box. And in permutation, this operation involves rearranging the bit within the data block according to a specific permutation pattern, named P-box. In Feistel network, we focus on substitution and mixing via XOR operation with the round function. Permutation is not explicitly required in Feistel network, as the swapping of the half during each round provide diffusion. In SPN structure, K-mixing typically involves XORing the round K with the data block. And in Feistel network, the K-mixing is achieved through XORing the round K with 1/2 of the plaintext during each round. And concerning the decryption process, in SPN, the decryption required the inverse operation of substitution, permutation, and K-mixing. Applied it in reverse order to the ciphertext. And for Feistel network, we use the same round function for decrypting data and subkeys as the encryption process, but apply them in reverse order. Here we give the characteristic of the two platforms chosen for the test. Raspberry Pi is a low-cost credit card size based on ARM Cortex architecture. As we can see, the Raspberry Pi has a limited resource compared to a normal PC, so it is a good choice for developing IoT project and application. This table summarizes the execution time obtained for each algorithm. In the Asus PC, for 64-bit block size and 128-bit key size, we can observe that some lightweight algorithms such as Simon, Spec, and XTA, which are based on Feistel structure, require less time for encryption and decryption. The fastest algorithms are Spec and Simon. Other algorithms such as Present and Skinny, which are based on SPN structure, require more time for encryption and decryption process. The slowest algorithm is Present. This table summarizes the execution time obtained for each algorithm in the Raspberry Pi 3 Model B. For 64-bit block size and 128-bit key size, we can observe that all the algorithms show the same performance with small increase of the encryption and decryption execution time compared to those obtained in the previous test. This is due to the limited characteristic of this platform. Spec and Simon are the fastest algorithm again. Present is the slowest algorithm again. So, as a result, Feistel network tend to have certain advantage that can contribute to their perceived speed. Feistel network process the 2/2 of the plaintext independently in each round and have the simpler structure compared to SPN. The simplicity of the structure can make it easier to implement efficiently, potentially resulting in faster execution. And as conclusion, the algorithms which are based on Feistel structure show the fastest time, and the algorithms which are based on SPN structure show the slowest time due probably to the use of transformation function, substitution S-box, P-box, round K, etc. The speed comparison between the two structures depend on specific algorithm, their implementation, and the hardware or platform used for encryption and decryption. It's essential to consider various factors and conduct performance evaluation to determine the relative speed of specific instance of this cryptographic structure. Thank you for your attention, and if you have a question, please write it in the comment. Thank you.